Low-light images are a nightmare for detail and noise. Deep learning has made massive strides in fixing this, but there's a persistent problem: control. Most enhancement models are binary. They learn a fixed mapping and give you one output. You can't dial in the brightness. And while large generative models like FLUX can restore images, their generative nature often introduces hallucinated textures or structural drift, which is a deal-breaker for restoration tasks. A new paper from NeurIPS 2026 called ControlLight solves this. It introduces a framework for continuous, fine-grained, low-light enhancement that preserves structure, generalizes to real-world scenes, and lets you adjust the enhancement strength smoothly from 0 to 1. Let's break down exactly how they achieved this, from the dataset construction to the loss functions. The core limitation of existing methods is the training objective. Traditional approaches like Retinex or SID-net are trained on paired datasets with a single target per image. This forces the model to learn a fixed enhancement strength. On the other end of the spectrum, large image editing models rely on text prompts. While they have strong priors, they lack fine-grained control and can easily hallucinate. ControlLight sits in the middle. It leverages the generative priors of a large model, but enforces continuous control and structural consistency through a new dataset and a novel loss function. To train a model for continuous control, you need continuous supervision. The authors construct Light100K, a large-scale dataset of real-world degraded low-light images paired with pseudo-enhanced targets at varying strengths. Generating these pairs is tricky. They start by collecting real low-light images and using a pre-trained FLUX LoRA model to generate a normal light reference. However, you can't just blend these images to get intermediate strengths. A naive approach like alpha blending in RGB space mixes illumination, reflectance, color, and local contrast. This tends to flatten shadows, weaken local contrast, and create artifacts that don't match real-world degradation. Instead, ControlLight uses a Retinex-inspired interpolation strategy. The Retinex model decomposes an image into reflectance and illumination components. The key insight is that continuous enhancement should primarily be a transition in the illumination component, not a direct interpolation of the whole image appearance. Here's the technical breakdown. They convert the low-light image I0 and enhanced target I1 to linear RGB. They estimate illumination maps L0 and L1 using edge-preserving smoothing on the luminance, and derive reflectance maps R0 and R1. For the interpolation, they work in the log domain for illumination. The intermediate illumination LS is computed as LS equals X, 1S log L0 plus slog L1. This is equivalent to multiplicative interpolation, LS equals L0, 1S, L1S, which is physically more consistent with illumination changes than additive blending. For reflectance, they use a conservative interpolation RS, 1 beta S, R0 plus beta S R1, where S equals S. This avoids relying too heavily on the noisy reflectance of the low-light image, while also preventing the model from inheriting artifacts from the diffusion-generated target. The final pseudo-target is reconstructed as IS equals clip, RSLS. This creates a trajectory where brightness transitions naturally, while preserving local shading and texture. Now, even with this careful construction, diffusion-generated targets can contain subtle pixel-level edge misalignments with the input. These misalignments are hard to see in RGB space because the dominant differences are brightness and color. But if you train with standard flow matching, the model treats all spatial regions equally. It will try to reproduce these misaligned edges, causing structural drift and artifacts in the output. To fix this, the authors introduce the Misalignment-Aware Weighted Flow Matching Loss, or LWFM. The goal is to anchor the enhanced output to the input structure, while allowing the appearance to change. They compute a structural edge difference map to isolate high-frequency structural discrepancies. First, they convert images to the log luminance domain and remove slow-varying brightness by subtracting a smoothed version, isolating the high-pass structural component. They then compute a high-frequency edge response using the gradient operator. The edge difference map between the input and target highlights regions where the structure has shifted. Based on this, they generate a weight map. For each pseudo-target, they compute binary edge maps for both the input and the target. They calculate the distance transform from the input edges. If a target edge is far from any input edge, it's flagged as unreliable. This creates a mask that identifies regions where the target structure deviates from the input. This mask is converted into a soft weight map that downweights the loss in unreliable regions. In standard flow matching, the objective minimizes the difference between the predicted velocity field and the target velocity. With LWFM, this objective is reweighted by the spatial weights. The model still receives weak appearance supervision in mismatched regions, but it's no longer forced to exactly fit misaligned pseudo-target edges. This significantly reduces structural inconsistency and prevents the amplification of artifacts during training. With the dataset and loss in place, the architecture is relatively straightforward but effective. ControlLight is built on FLUX LoRA 9B, fine-tuned using LoRA. The control strength S is incorporated directly into the LoRA scaling factor. The effective weight matrix becomes W equals W plus S ob, where W is the frozen base weight and A, B are the learnable low-rank matrices. This design differs critically from methods like concept slider, which optimize a LoRA direction via text-guided score matching and assume linearity at inference time. In ControlLight, the linearity is enforced during training. Each strength value S is paired with a specific pseudo-ground truth, and the loss is computed against that target. The LoRa direction is calibrated against a physically grounded illumination trajectory with per-strength supervision, which is why the model achieves such smooth and linear control. The results speak for themselves. ControlLight is evaluated on both paired benchmarks like LOLV1 and LWSR, and real-world unpaired datasets like DICM, LIME, and RealIR-Bench. Because generative models can produce perceptually plausible details that might penalize reference-based metrics like PSNR, the authors focus on non-reference perceptual metrics like ClipIQA, MANIQA, and MUSIQ. ControlLight achieves state-of-the-art performance across most metrics, significantly outperforming traditional methods like Retinex and SIDNet, as well as continuous editing baselines like CLE diffusion. On real-world benchmarks, the improvement is particularly notable, demonstrating strong generalization to natural degradations. To evaluate the continuous control specifically, they use the smoothness metric delta smooth and the semantic directional consistency metric clip-dire. ControlLight shows excellent smoothness, meaning the enhancement trajectory doesn't jump or oscillate as you vary the strength. The clip-dire scores confirm that the enhancement moves consistently in the right semantic direction, away from underexposed semantics. Ablation studies confirm the necessity of each component. Removing the weighted flow matching leads to higher structural inconsistency and lower perceptual quality. Replacing the Retinex interpolation with alpha blending results in artifacts and a degradation of the quality gradient, proving that the physically grounded interpolation is essential for learning a robust enhancement mapping. ControlLight represents a solid step forward for controllable low-light enhancement. By combining large model priors with physical constraints, a carefully constructed continuous dataset, and a loss function that explicitly handles structural misalignment, it delivers fine-grained control without sacrificing realism or consistency. If you're working on low-light restoration or controllable editing, this is a framework worth studying. The code and dataset are available via the project page linked in the description. Thanks for watching, and I'll see you in the next one.